Welcome to Statistics Chapter 5, Lesson 6. More about multiplication rules and tree diagrams. So, example 1. Many people choose to have annual mammograms to screen for breast cancer after the age of 40. A mammogram isn't foolproof, though. Sometimes the test suggests that a person has breast cancer when they do not, and that's called a false positive. Other times it suggests that they do not have breast cancer when they actually do. That's a false negative. Suppose we know the following information about breast cancer and mammograms in a particular population. 1% of the people aged 40 or over in this population actually do have breast cancer. For people with breast cancer, the probability of a negative mammogram is 0.03, or 3%. And for people who do not have breast cancer, the probability of a positive mammogram is 0.06, or 6%. So if a person aged 40 or over is randomly selected from this population and they test positive for breast cancer, find the probability that they actually have the disease. So let's make a tree diagram to look at this first. So they're all from the same population of over 40, and there is a 1% chance, 0.01, that they have breast cancer. Which means that the other 99% do not have breast cancer. Of those who have breast cancer, the probability of a negative mammogram, again, that would be a false negative, is 0.03, 3%, which means that a true positive is the other 97%. And then of the people that don't have breast cancer, they could have a false positive, which would be the 6%. And then a true negative would be the other 94%. So let's do some multiplication and find out the actual probabilities of getting a true positive, false positive, and true negative. So again, we just multiply it down the lines. So 0.01 times 0.97, there is a 0.0097 chance that there is a positive. And 0.01 times 0.03 should be 0.0003. Very, very small number. As for those who do not have breast cancer, 0.99 times 0.06 is a 5.94% chance that they are show up in the selection. And then finally, 0.99 times 0.94, 0.9306. So they do test positive. Find the probability that they actually have the disease. So we're kind of looking for a true positive chance out of any positive. So the true positive chance was that 0.0097, and any positive chance would be both the true positive and the false positive added together. So let's see here, 0.0097 plus our 0.0594 is 0.0691. So if we take our 0.0097 and divide that by our 0.0691, then we get there's actually only a 0.14 chance if we round to 3 decimal places here, or 14.038%. One of those. And that's example 1. Example 2. On January 28th, the Space Shuttle Challenger exploded after takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions on that day, experts estimated that the probability of an individual O-ring joint would function properly was 0.977. But there were 6 O-rings, and all 6 had to function properly for a safe launch. Assuming that the O-ring joints succeed or fail independently, find the probability that the shuttle would launch safely under similar conditions. So the probability that they launch safely, so we could do a giant tree diagram where ring 1 succeeds or ring 1 fails, where there would be a 0.977 chance of success, and then 1 minus 0.977 would be a 0.023 chance of failure, and then we would go to ring 2 succeeding, ring 2 failing, from there ring 3 succeeding, again with our 0.977s all along the branch there, all the way up to ring 6. Now, that might take up a lot of space, and we're just looking at what happens when all 6 function properly. So that would be 0.977 times itself 6 times. So our probability of success, we can actually take a shortcut here by taking our 0.977 to the power of 6, and we get 0.8696 rounds about to 0.87, or there was actually on that day an 86.97% chance, because again this 5 bumps that 9 up to a 10, which bumps that 6 up to a 7. There was an 86.97% chance that it should have worked, but unfortunately we know it didn't. Example 3. Many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn their test results. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example, the use of rapid tests has increased the percentage of clients who learned their test results from 69% to 99%. The trade-off for fast results is that rapid tests are less accurate than slower lab tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004 of producing a false positive. If a clinic tests 200 randomly selected people who are free of HIV antibodies, what is the probability that at least one false positive will occur? Assume that the test results for different people are independent. So if we have 200 tests where the two options are 199 of them are true negative, and only one of them is a false positive, then the probability of a true negative would have to happen 199 times, and that would be 1 minus 0.004, or about 0.996. And then the false positive, again, is still our 0.004. So we would need the probability of at least one false positive is going to equal that 0.004 from 1 false positive times 0.996 to the 199th power for the other 199 true negative scores. So 0.996 to the power of 199, and if we multiply that by 0.004, we get that there's actually only about a 0.2% chance. 0.002, or again, about a 0.18% chance. So we can use exponents to speed up very large, long strings. And then finally, example 4. Hacienda Heights and La Puente are 2 neighboring suburbs in the LA area. According to the local newspaper, there's a 50% chance of rain tomorrow in Hacienda Heights and a 50% chance of rain in La Puente. Does that mean that there's a 0.25 probability that it'll rain in both cities tomorrow? Well, since they're right next to each other, no. Since the same rain clouds will probably be over both cities at the same time. If they were independent rain clouds, then yes. But since they're the same rain clouds, then then we don't need to multiply those two percentages together. It's actually the same 50% for both cities. Again, these are not 2 independent events, or they are not 2 different independent events, so we don't need to multiply the probabilities. And that was section 6. Your homework, as usual, is up on Canvas, and we will have a test on this soon.